Welcome. My name is Owen Moore, and I'm a creative developer and artist. Today I'm going to be talking to you about my curated project, Flux, and go into some of the details that make up this audiovisual experience. The topics that I'll be covering today include signed distance functions and Raymarching algorithm. I'm going to go into some live coding experiments to show you the steps along the way that led me towards discovering the technique I'm using in Flux. Lissajous Curves for motion, and I'll go into some of the audio such as the chords, the tonal range, synthesizing audio timbre, and ultimately how I brought it all together to make the visuals that you see on screen influence the actual audio being synthesized. So to start, I'm going to start with the signed distance functions. Basically, it's a mathematical description of a 2D or 3D object. It can actually be in more dimensions, but they become obviously a lot more difficult to visualize. But in the end, basically, it's a function that returns what's called a signed distance. So think of it, you are 1 meter away from something in your room. You are positive 1 meters away from the object. If you were, say, inside of a fridge, you'd be negative distance inside of the object. And if you are touching the object, you're at 0. That would be a hit. I'll show you some demonstrations of this in just a moment, but basically these kinds of functions are suitable for primitives like boxes and spheres and other very simple objects that can be described mathematically or in equations. And so if I go to this article written by Egino Quiles, he's shared with the community a lot of functions that you can use to describe some of these primitives, such as a sphere, a box of various sizes, a torus. And from all of these, you can construct some pretty impressive scenes. If I go to some of his work on Shader Toy, which is a website that he helped create, you can kind of see a bunch of these scenes that have been created using these primitives and stretching them out, adding colors to them. And you can do some absolutely incredible work, and this was something that I was researching early on. And so specifically, here's a scene that shows a number of the basic primitives. Now, as I'm going around this, it's quite choppy, so it's not just the video recording that you might be seeing. It's a very expensive type of rendering technique, so you wouldn't necessarily use this for a video game or something like that, though you absolutely could in certain scenarios. But it's more of just like a graphics technique that you can use for interesting forms of visualization. And I'm not totally sure where the actual practical application of this is, but in terms of art, you can do some absolutely amazing work with this. And so, if you take a Mandelbrot, for example, you can use a similar technique to visualize what that looks like. This technique. And so, how do you actually use these equations? Well, you basically visualize them through what's called the Raymarching algorithm. And what that does is it starts at a position where you could say your ray origin or perhaps your virtual camera, and you look towards your scene and you take a measurement. Well, what is the closest distance to any of the objects in scene? And then you move forward, and then you do it again. What is the closest distance? Move forward that distance, and you keep going until you've basically got to a point where any step forward is almost too small to be measured. And if that occurs, you assume you've hit the object, and you tell your shader to draw it appropriately. So if you wanted to draw everything all gray, you would say, okay, make this pixel gray, but if you missed it, you would draw it black, for example. And so let's take a look at what that kind of looks like in practice. And so here you see the same diagram I was kind of showing, but somebody on Shader Toy has made this fantastic visualization of it. So if I click here and drag out, you can see this is where it's shooting out those rays, and you can see each of the distances updating for each of the steps. Now, important point to notice is that this particular one is taking 4 steps, 1, 2, 3, 4. but it ends without hitting the object even though we know it should. So when you're crafting these functions, you need to actually create quite a lot of steps. So for this one, I'll stop at 16. And you kind of define what is the smallest increment that you want to measure, and if you have hit a step that is moving in less than that, you consider that a hit and you draw your object. And it's kind of, you can think of it like it's not a super accurate hit in that it's not scientifically correct, but it, for the purposes of rendering a colored pixel on screen, this is more than sufficient. And so let's take a look at another scene here. And so you can see it's quite versatile. So if you place the camera over here, you can hit all these objects up until the ray shoots way past. And that would be an example of where you do not hit something in the steps that you've defined, and so thus you draw black or a gradient or whatever it is you want to consider a miss. But you can see, you know, from any which angle, it kind of functions as I've been describing. And so the important thing in mentioning that those steps is that they're quite computationally expensive. So if you had, let's say, 1,000 steps into your scene, that would slow your graphics card down and potentially cause a crash if you've run out of memory. And so the thing that I learned as I was educating myself on this technique is that there are ways to optimize your scene. So for example, here on the left, this red image is visualizing those steps. So this blue means, okay, maybe it only hit the object after 1 or 2 steps or something like that. But red means it took, let's say, 255 steps for it to actually accomplish. That would be a huge amount of wasted computation power to hit these pixels that should basically be black or your background. Over here on the right is an example of something that would be a tuned scene where you've found a sweet spot where it's doing some steps around the object, and you can see there's a bit of a glow because as it's getting around the edges, it takes a lot of little steps before it actually shoots past it and realizes, oh no, actually I've missed. But this is much more optimized. And so the important thing I'm discussing in bringing this up is that this is one of those things where, as I get into my live code experiments, you'll see I discovered a technique by kind of hacking around a very small number of steps. And so with that, I'm going to jump into my code experiments. So to begin, I'm going to walk you through some examples of these SDF functions working with the Raymarching algorithm. So on the left here, I've got some code, and on the right, you'll see whatever it is that the code is rendering. So at the moment, it's got a torus out in space, not doing a whole lot. If the ray misses, I've drawn a gradient in the background. If it hits, it calculates some lighting and presents you with the object. So I've also added some mouse movements, so you can see that it is indeed a 3D object. You can rotate it, have a look at it from different angles. All of these things are possible with the method. And so you can do things like make it a whole lot chunkier, or a little thin, or perhaps it's a larger ring. And so, you know, you have the freedom to kind of shape and manipulate these different objects. Another technique that I learned was actually to take this object and twist it. And, you know, I don't know what a whole lot of use is for a twisted up torus, but it kind of looks interesting. And if you add a little bit of time to it, you can have it shifting over time, which produces, you know, something quite interesting to look at. And then you have other, you know, more simpler objects, like such as this cube. You know, it's kind of fun to rotate it around, to look at it and see it shine as the light casts over it. But then you also have functions like this that you could combine the different objects. And so if I make this a lot more sharp, you'll kind of see a little more clearly that you've got this cube meshed in with the sphere. And of course, the animation is still going live. If I stop moving the mouse, you can see it kind of morphing in and out of the cube. And so really, at this stage, I was just kind of experimenting with what you could possibly do. And if we bring that morphing way down, it produces kind of this nice, nice blending. Oops, I stopped it. There we go. And so I was kind of just curious. I'm like, okay, well, this is interesting. What could I maybe do if let's say we took two different toruses with twisting. So this one is thin. It's very twisted in this direction. And the other one, let's say it twists in the opposing axis, and it's a lot thicker. What would happen if I took those two and combined them? Well, when I saw the results, I thought, okay, now I've got something interesting. I've got these negative spaces inside of the object that kind of appear and disappear. It kind of feels like it's maybe a gum or some sort of oozing liquid in space. And I wanted to explore that a little farther. And so I'm just going to undo all this for a second. There we go. So as I continued to experiment, I started thinking about that optimization problem. And so right now I've got it set at 128 steps, which, it's okay for my current laptop, but I was running on a much older one at the time that could barely handle this kind of sampling. So I started dropping it down. Okay, 64, that looks okay. But there's a little bit of pixelation. But maybe that's okay. Maybe I'll just continue going down. 32. And that's when I started seeing this appear. And this is no surprise if you've, unoptimized your scene. But basically what's happening is as the ray shoots past the object, it's run out of rays to continue off into infinity. And it's within a threshold that I've kind of manually hacked into the function to display. This isn't necessarily a correct way of rendering this, but it's hitting a threshold where I'm kind of forcing the function into saying, okay, I think I've still hit, even though it's warped around on the opposite side of the object. And so I continued doing that until I got this really interesting gradient where it's sampling not just the front, but the backside from both around the outer edge and through the inner edge. And I wanted to see what I could do with that. So if we start rotating the object again, it produces something kind of interesting to look at. Maybe not the most impressive at the moment, but this was kind of the starting point for me to discover what I could do with kind of breaking the Raymarch function. And so here's the twisted torus, for example. And now that starts to feel very liquid and in motion and very interesting as you move it around. Even the cube, it can produce some pretty interesting looking results. I may come back to more solidified primitive shapes for a future project or something, because I quite like how the shine kind of appears and disappears from the space. But then I wanted to get all the way to the mixing of the two tori together. And that's really the image that sold me on exploring this technique further that I discovered. Once you set it into motion, that's where it really kind of starts to resemble what I have for Flux. Now, obviously, there's a lot of elements that I would say are different, but this is very much the starting point that got me curious. And as I saw different patterns evolve, such as these like little squares from the hole through the object, I knew I wanted to do something with it. And so I kind of went back a little bit to the drawing board and I started experimenting with different shapes, applying colors in different ways, different gradients, different, for example, the object, if it's facing down, it'll be a particular color. If it's facing left, it's a particular color. And just wanting to see what these kinds of shapes might look like using that technique. And so these are just completely random. And if I were to, move it around just to see what it can do, this is kind of the next evolution of what I did to see how I could use this technique to build something interesting. Originally, I thought maybe I would let people interact with it like this, and while it's quite fun, it didn't end up fitting the narrative that emerged from this project. But there's some like this I didn't quite like. These I like, but perhaps they're a little too simplistic. These are quite interesting. And these kinds of experiments are what led me to discover what kind of range of variables that could be fed into the different tori thicknesses, sizes, rotations, merging, all those kinds of things. And then I kind of continued on with some other experiments just to see what I could do. For example, this one creates like a bit of a repeating loop. Kind of made like a little bit of a tear shape. Some negative space in the middle. And then I started putting some math equations in, and I put in a sine and a cos for a particular value, and then of course it came out with a circle, and I kind of accidentally just made the torus again, which was quite humorous to me. But then I tried, what if I just had some of those math equations repeating? It kind of creates this banding effect. You can't really see too much in this one, but if I made just the sine plot, I wanted a sine wave going up and down the screen, and really just kind of seeing how well these things visualize. And then I threw together some crazy sine, cos, and tan combination, and this popped out, which was wildly different than what I was expecting. And if you're familiar with my work, I hope you'll recognize that this is probably the starting point of quarantine. And so the reason I'm sharing this is just to show that as part of experimentation, you can have branching paths. Basically, as soon as I saw this, I didn't discontinue working on Flux, but I wanted to explore this further because it produced such interesting results. Now, again, back then I was running on a much older laptop, so I didn't think to animate this because this was near impossible at this speed, but kind of wish I had explored it more, because this is so much fun to play with, seeing the expanding contraction of this space. And if you want to get a sense of what this actually is, basically the equation I came up with created these tiny little pill shapes in an infinite field. Now, I'm kind of culling them based on how far or close they are to camera, so they pop in and out of existence in a repeating fashion. You can see them kind of cascading away. Then I moved on to trying it with different time applied, so cycle in and out. And I won't spend too much time on this particular one, but it did eventually become what I built into Quarantine. And so moving on, this is basically what I consider the prototype, the one that, after manipulating a bunch of values and kind of dialing in some randomized colors, and as you can see, I can shift the colors, and certain things kind of come in and out of existence based on the color blending modes. This was very much like the prototype, where I was like, yes, okay, I need to do something with this. This is interesting. If you put it into motion, again, I'm still controlling it with the mouse, but I ended up animating it in the final result. But if you move it nice and slow, it gives this liquid kind of motion. If you come across, and basically the mouse is just controlling the rotation of that object, and I'll show you that in just a moment. But it kind of really sold me on the concept. This to me was beautiful, and I needed to harness it. Now, if there was things like this where the shadows don't quite work out, the highlights kind of look weird, this gets blown out, so there was a lot of creative work to be done. But the general principle of having an underlying shape be unwrapped through this process was what sold me on the concept. So as you can see, kind of here's the underlying 3D object that is actually being rendered flat through a series of basically short-circuiting, the Raymarching algorithm. So I'll cycle through a few of these because it's kind of fun to look at. And so now that I had this prototype, and obviously with a bunch of refinements, I wanted to animate it. Now, originally I was controlling it with the mouse, but I felt that having it be an experience that you can kind of sit back and relax and watch would be more valuable. But I really wanted it to cycle, and that's where using a technique for Lissajous Curves kind of comes in. So as you can see on the right here, and I'll show you a demo in a moment that gives a much better idea, but basically you're taking a sine function and changing the frequency with which it's cycling from -1 to 1 or 0 to 1, depending on how you map it. And here you've got a pi over 4 with a 1 to 2. You kind of create these patterns or these, and you can create some really interesting patterns. But the point is, like, for example, this one, the position over time will go like this and then bounce back and come back. And so it creates an infinite position. And if we go back to the art here, the mouse is controlled within the boundary of the image. He can't get a value beyond the pixels that you see here. And so if I trace it kind of following a figure-8 pattern, now obviously this is far too fast for the actual artwork, but it creates an interesting motion. And if you keep doing that figure-8, eventually you'll come back to the same position. And that's really what I was trying to go for. The good thing with these is they're very easy to take, let's say, a 0 to 1 range and map it to, let's say, 2 degrees to 34.85. You can map that in code quite easily. And so if we come back to our demos here, this is a demo somebody else had created. I don't recall who, but it really shows you the different periods of this circle being created. So down this center here, the important thing to note is that if you have the same speed for both of them, you'll result in a circle every single time. So effectively, I have two different functions that run, and I ensure that they are never running at the same speed. But these are the kinds of patterns that the XY value are being mapped to the actual rotation in Flux. So I have mint0 from Flux loaded up, and it's a good case to show you because it actually uses a figure-8 pattern and doesn't take too long for it to actually cycle through. So I'm going to turn on debugging mode. Now, this point here is basically representing within the ranges of the image how far to the left or right that Lissajous curve has been calculated, and then that is being fed into the rotation of the object underneath. And so I'm going to make it a little bit, oops, wrong one, sorry. Going to make it a little bit darker so it's easier to see, and we're going to hit play. And so you can see as it's moving, it'll start to move up to the right and eventually start building out a figure-8 pattern. While that's doing that, I'm going to make it go into a ludicrously fast speed, just so we can see this a little faster. Now, of course, this is going to be ridiculous, but pay attention to the dot. That's where, I'm trying to show you that it's drawing a figure-8 pattern. And so if we just start generating some random ones, we should start seeing different patterns. Maybe that's a little bit too quick. So I felt this was a great way to create repetitive motion that also kind of explored the range within the rotational values of the underlying object. Now, interestingly, I don't actually know how long the actual artwork could theoretically take to loop. I have watched a number of them, and I believe it's somewhere between 5 minutes and 30 minutes, depending on the exact variables. knowing exactly when it loops isn't really the point of the art anyway, so I'm not too terribly concerned about knowing that offhand. All right, let's undo a bunch of that. And we'll go back to our notes. And so now I want to talk about the musical qualities behind this, the chords and the tone range. Now, I experimented with a number of different chords, majors, minors, augmented. I'm not a music major, so I couldn't go beyond that. But basically, what I landed on was just leaving it with the major chords because they felt very bright and happy, whereas a minor is a little more melancholy, or others just kind of feel odd to the senses, and I wanted this to be a calming experience. So I had put in all of the major chords, starting at a kind of a mid note that you would expect to hear from a guitar or a piano player. But what I needed was a lower and higher frequency. It felt a little too empty. And so I added one octave lower from the root note. So here in C major, the root note is this C1. And I added a octave higher for the remaining two notes. So the C major chord kind of became what I call the expanded C major. Maybe there's a technical term for that, I'm not sure. But essentially you would have a nice deep note that complements the next note up, and then these four kind of complement each other. And you had a nice tonal range that wasn't too high and buzzy, not too low and rumbly. And so then I started thinking about how could I map this to the actual art being displayed. I really wanted them to be in sync in some way. And the first thing I came up with was basically mapping the notes to the particular regions on the screen. And so note 0, which would be this C0, through note 1, 2, 3, 4, 5, would be in order of this chord. And so this band is always sampled from the actual art being rendered to determine a bunch of variables, but let's just start with the volume. So for example, the C0 note volume would be tied to here and going down. The reason I put them starting from the top to bottom was that, generally speaking, all of the art tends to be brighter at the top and then fizzles out towards the bottom, a darker region. And so that way I would always have a nice low rumbling sound, but then on a much brighter visual, you would get some higher pitch frequencies kind of coming in and out and fading as the art has pixels being rendered at a brighter value there. And so that's what I needed to learn how to do some texture sampling. And so I'm going to set it up so we can see the texture being rendered. So I'm going to turn off a bunch of post effects, which basically I'll cycle between them because that's kind of interesting to see. Like some glowing, some minor adjustments for the contrast and saturation, a little bit of vignetting. And so now we're just seeing the raw render directly from the first pass. And so if I instead switch it to render the sampled texture, we'll see it turns black and white and very low and pixelated. So the texture, it samples at a much, much lower rate than the actual resolution of the image being rendered, and it stays at the fixed resolution. That way, as the art scales up and down, no matter what, the texture will always be the same amount of pixels being read and sampled to feed into the actual audio synthesis. So if I play it, you'll see everything operates just the same. It's just a very low resolution and black and white. It's actually not black and white conversion. It's measuring the luminosity of the pixels in the image. And again, if we just generate some random ones, you'll see, this one's quite dark in the bottom. That would probably sound a little deeper in tone. Let's see if we can find a bright one. So this one probably has some higher pitches. And so there you go, you can hear some of that resonance at the top end of the audio. And this one will more or less have the highest portion cut out. The deeper notes will be tuned down a little bit, and the midsection might sound a little more clear. And that's where you're getting kind of some of that conflicting vibration, because there's maybe a little bit too much going on in the mid-range, which is okay. But just trying to show some of the diversity here. And so next I wanted to... Now, the final product you're hearing right now has all of these factors combined, so I didn't have... it would be too difficult for me to isolate some of this. But you could imagine as I was creating this would be like if you jammed on the keyboard and each note could be turned up and down. It sounded okay, but there wasn't that nice buzzing and harmony that you kind of hear in the final product. And so that's where synthesizing audio timbres comes in. Now, a timbre is a way of describing a particular note can sound all sorts of different ways. If you play the same note on a guitar or a piano or a violin or any other instrument, really, it sounds different, even though it will have the same underlying frequency. And so I play with synthesizers and I play guitar, but on the synthesizers, they have these different wave shapes that create different sounds. You know, there's this triangle wave, a sine wave, which sounds much more smooth, this very harsh saw wave, which is used in a lot of electronic music, or same with the square, creates kind of like the like old school 8-bit video games uses square waves because it's a lot cheaper to pack that into a synthesizing engine. And so when you have a synthesizer, you will mix different waves with different amplitudes, frequencies, all sorts of other things, and you create a unique timbre out of it. And you can do a lot with that, from making it sound like a shooting laser to a nice, soft, calming wave. And so what I wanted was not to necessarily use these, though. I wanted to create something that's called like a wavetable, where you would have something, let's say, like this, and you could blend between one to the next to create a range of audio timbres. And after doing some research, I found that the library Tone.js that I was using has a feature called partials, which kind of acts like a custom wave shape. So when you hit the note, you could say, okay, the frequency is like up, down, up, down, up, down. You have different ranges for it. And so it uses a technique called additive synthesis. And I'm not going to go into how exactly this works, so I'll just kind of show you this great article I found, and hopefully we can link it into the notes. But in short, additive synthesis just kind of plays on the phenomena where you have waves. So if you have waves on an ocean, one large wave will combine with a small wave, and you'll see the ripple go up and down over the large wave. So if you see here, there's this lower frequency sine calculation and a higher frequency, which combine to make this unique wave. And as far as I understand it, you can basically craft any audio by just manipulating these different frequencies. And kind of want to scroll down and show this diagram, because this is a great way of explaining what a partial is. So if you have a frequency that's 0 to 1, the next partial would be 1/2, and then 1/3, 1/4, 1/5, 1/6, 1/7. And it's a way of kind of cutting down different additive sine waves such that you can actually do something interesting with it. And if I come down all the way to the bottom here, I just want to kind of show you what something may sound like based on this technique. And so now that might sound a little bit harsh, and I didn't want to use it exactly as that, but this kind of article helped me realize, okay, that's how I could create some harmony that hits a note, but also has oscillating frequencies that kind of come in and out. And what I thought was maybe I could use this to craft some unique notes in some way. Now, this person also has this fantastic visualizer, and if I unmute it, you can hear that now we're just hearing this sine wave like I was discussing earlier. And if I switch that over to a square wave, you can see how it's combining the different frequencies together to kind of add up to this high, and then jumps down to low, and jumps up to high, jumps down to low. And if you do this at a high enough frequency, it basically becomes almost like a digital signal. It's obviously not. You can see it wiggling here, but it's close enough for our purposes. And so if you recall back to this previous slide, I had the notes in these horizontal bands being sampled from the image. And I decided to chunk them into averages of each of these little sections, 1, 2, 3, 4, 5, 6, 7, 8, 8 of them, and use those to describe the partials from the base frequency here on the left all the way to a high frequency on the right. Now, I didn't do that in any particular order for any reason. It just was a logical order to do it in the code. But basically, each note horizontally has its own oscillator, like that application I was just showing you. And then each of the chunks' luminosity values will change up or down the different frequencies down here on the left. So you can imagine it's mapped to each of these. And because the visuals will change over time, these will shift up and down and all around. Maybe not all around, just up and down. But that way the image would then actually directly impact not just the overall volume of that particular note, but it will also impact the shape of the overall sound. So if you watch some of the art that have particularly high luminous values along with dark ones, you'll kind of hear the tones shifting from high to low. Let's say if it goes across the screen from right to left, or low to high if you go from left to right. And having these all layered together in a chord creates a lot of the hidden harmonies that kind of add together, because all of those other notes, again, are additive together to produce the actual audio coming out of your speakers. And so once I had that set up, there was just, little bits of details to bring it together. And I, again, took those bands that were used for the notes and used a technique that's quite common in using synthesizers, which is to detune each note. So I kept it very, very subtle, but by moving at a few cents left or right from the actual note, again, creates a little bit interesting imperfections. If you just had perfect tones all over the place, it would sound awful. It would sound like a computer made it. But if you have it detuned, it sounds like maybe you have an instrument that's not absolutely 100% perfectly tuned. Then I use the overall luminosity of the entire image to feed into a low pass or a high pass filter. Now those are basically filters that say frequencies above, let's say 800 hertz or whatever, are going to be ignored. So that way you kind of get rid of some of the buzzy noises that kind of result from mixing so many different values together. And also you get rid of some of the lows where you have a deep rumbling bass kind of popping in and out of existence. But what I ended up doing was tweaking that even further, just from a pure quality of life perspective, such that if the image was particularly bright, you would get this high frequency. The low pass would move up the frequency chain, kind of cutting out possibly a couple of the notes, and it would give it almost this ethereal feel, like a heavenly kind of image where it's beyond your recognition. Whereas the opposite direction, if your image was quite dark, it would be very low. And at the end, I just added a little bit of reverb to add some atmosphere. So I'll kind of show you what that may sound like in practice here. So I'll go back to my mint to 0, and what I'm going to do is over time it's going to go from light to dark, and you should be able to hear the shift within that. Now this particular mint, basically you'll hear it more in the high range, but if we invert the image, so think of it this way, you're feeding the opposite data to the audio. And so down here in the bottom, this light image means more low tones will sound. So now you can hear more the low cutoff. Now it's not too drastic, but if we just start randomly picking some other ones, maybe we'll hear something interesting. push it to the extreme and maybe slow it down a little bit. Or does that speed it up? I can't remember. No, that was the wrong way. There we go. Now, of course, this is extreme and exaggerated, but depending on the exact qualities that came out of the individual pieces of art, there is a very subtle difference depending on the overall luminosity of the piece. And actually, I kind of like some of that inverted as an aside. That would be kind of interesting. But alas, the project has already been dropped, so. And I think that's it for now. If you have any questions or want to learn more about the work that I do or Flux, please check out my website at owenmoore.xyz or hit me up on Twitter or Instagram at owenmoore_xyz. And yeah, thank you very much for listening. I hope you've enjoyed this presentation.